Hi everybody, the purpose of this video is to go over section 7 of chapter 8, and in this section we will be introducing the polar coordinate system. Yep, and that's it. That's what we're going to do. We are going to introduce the polar coordinate system. We are going to talk about how to convert from rectangular coordinates to polar coordinates. We will talk about a few polar equations and some plots of polar equations. And then we will conclude with an example on how to convert from polar coordinates to rectangular coordinates for a particular equation or point. Okay, so we are all familiar with the Cartesian coordinate system. It has an x-axis, which is typically horizontal, a y-axis, which is typically vertical in our plane. The polar coordinates consists of a point called a pole, which will typically sit at the origin of our Cartesian system, and then a ray which is called the polar axis, and here it is. The polar axis usually starts at the pole, which is typically at the origin, and then goes along the positive x-axis. So let's say that we have a point with rectangular coordinates xy. Here it is, and here's the point xy. Then it will have polar coordinates r theta, and the two coordinates can be related as follows. X can be related to r and theta by the usual projections of the trig functions. X is equal to r cosine theta and y is equal to r sine theta. And then r and theta can be related in the exact same way that we related r and theta for complex numbers. Namely, r will be equal to x squared, r squared will be equal to x squared plus y squared. So it is a direct application of the Pythagorean theorem. And then theta will be that angle that satisfies the relation tangent of theta is equal to y over x, keeping in mind the quadrant that the point happens to be in. So once again, if the quadrant is in 1 or 4, we can actually use theta as is. Well, maybe if it's in 4, we'll have to add 360 to it. If the point is in quadrant 1 and 3, the value of theta is going to be the arctangent of this plus 180 degrees or pi or pi, depending upon if we're dealing with radians or degrees. Now, the one interesting thing about the polar coordinate system is that the coordinate r is not just limited to positive numbers. It can be any value between negative infinity to infinity, including negative values. Similarly, the coordinate theta is not just limited to 0 and 360 or between 0 and 2 pi. It can also take on any value on the real line between negative infinity and infinity. And that creates a couple of complications when we are doing this, when you are working with polar coordinates. And this right here is the first complication. Now we know that if we were operating in the Cartesian plane, in the Cartesian coordinate system, that there is a one-to-one mapping between a set of points, between a coordinate and a point on the plane. Every single point will have one and only one coordinate associated with it. That does not occur in the polar coordinate system. Every single point can have an infinite number of coordinates associated with that point. For example, here is the point root 2, root 2. It actually will have a magnitude or an r of 2, and its base angle is 45. However, not only will the coordinate 2 and 45 degrees describe that point, 2 and any angle that is coterminal with 45 degrees, such as 405, 765, and so forth, describes the exact same point. Furthermore, since r can take on negative values, we can actually have an angle of 225 degrees, and r can be negative 2, and that will move us back to this point, because if you think about it, this is 225 degrees. If r was positive 2, we'd be going in this direction, but if r is negative, we are going to go in the opposite direction, which would put us here. So not only can 2 and 45 degrees represent that point, or any angle that is coterminal with 45 degrees, negative 2 and 225 degrees represents that point, and also any angle that is coterminal with 225 can represent that point if r is equal to negative 2. So for one particular point, we have exactly one point we actually have one set of coordinates for the Cartesian coordinate system. So we have what's called a bijection. And if we are dealing with polar coordinates, there is an infinite number of points or infinite number of coordinates that can describe that one point, which actually tends to be a problem. Okay, and this brings us to our first example. Here we want to consider the polar coordinate or the point with polar coordinates -6 and 60. So the angle is 60 degrees, but but r is -6. And the question is, which graph correctly plots that point? Okay, well, let's actually take a look at this graph really quick. Notice here we actually have basically a polar grid. And also notice that each of these grid lines here is 15 degrees. 15, 30, 45, 60, 75, 90 degrees. So -6, so 60 is going to be 15, 45, 60. That is 60 degrees right there. Okay, so 660 is that particular point right there. However, -660 is 60 degrees, but then we're going to go in the direction, but then we're going to go -6. Now it would be 1, 2, 3, 4, 5, 6. That would be this point right here. And the graph that actually has that plotted is this graph right here. So that is the correct, so this graph correctly plots the point. This one does not because it's in quadrant 2. This one does not because this is actually 660, and this one right here is 6 -60 degrees. Okay, let's go to the next part of this. In here, we want to determine two other pairs for the polar coordinates. Now remember, if -660 is one particular point, then 6, the other point is going to be +6, and whatever angle is supplementary to 60 degrees. And the angle that's supplementary to 60 degrees would be 60 plus 180, or 240 degrees. So this is one pair. This is one other pair of polar coordinates that describes this point, and another one is going to be the coordinate whose angle is coterminal with 60 degrees, and that would be 60 plus 360, which is 420 degrees. So both of these coordinates go to the exact same point. And the next part is to determine the rectangular coordinates associated with that, and of course that is nothing more than the use of our conversion equations we discussed earlier. The first one is going to be that x is equal to r cosine theta. Once again, r is -6. That's going to times the cosine of 60. The cosine of 60 is 1/2, so this is going to be -6 times 1/2, which is equal to -3. And then here for y, that's going to be equal to r times the sine of theta, which is -6 times the sine of 60, which is equal to -6 times the square root of 3 divided by 2, which is equal to -3 times the square root of 3. So the Cartesian coordinate, or the rectangular coordinate, is going to be the coordinate -3, comma, -3, root 3. There you go. Okay, for our next trick, we are going to be given a pair of rectangular coordinates, and then we are going to choose the correct plot, and then we are going to find two polar coordinates that actually represent the exact same point. Now, the first part's pretty straightforward. We are going to go -4 in the x direction, and then +4 root 3 in the y direction. So -4 in the x direction, +4 times the square root of 3 in the y direction. That would be a point here. And the graph that displays such a point is this graph right here. So that's our answer. The next part is to determine two pairs of polar coordinates where theta is between 0 and 360, and there will actually be exactly two pairs. Now the first thing we need to do is we need to figure out what r is. And r is going to be the square root of x squared, which is negative 4 squared, or 16, plus y squared, which is going to be 4 squared, which is 16, times 3, which is 48. That is going to be equal to the square root of 64, which is equal to 8. So we have a value of 8 for r. Now to figure out the potential values for theta, first thing we need to do is to compute the arctangent of y over x. And y is 4 times the square root of 3. X is negative 4. This is going to be the arctangent of negative root 3. And that will be negative 60 degrees. Okay, so two possible angles, negative 60, so two possible angles are going to be negative 60 and the supplement of negative 60, which is 120 degrees. Now remember, this point is in quadrant 2. Okay, which basically means that the angle associated with that particular point is going to be 120 degrees. So one pair of polar coordinates which will go to this particular point is going to have a radius of 8 and an angle of 120 degrees. The other pair of possible polar coordinates that will go to the exact same point is going to have an angle that is supplementary to 120 degrees, such as negative 60 degrees, and is going to go 8 units in the opposite, in the direction opposite of that angle, which is basically negative 8. So that is the other polar coordinate that actually represents that particular point. Next, we want to talk about polar equations. Particularly, we are interested in converting rectangular equations into polar equations, and this is how it works. Whenever we see an x, we're going to replace it with r cosine theta. Wherever we see a y, we're going to replace it with r sine theta, and then we are going to solve for r. Okay, so now we want to find a polar equation for a line. And here we're going to use the linear equation, slope-intercept form of y is equal to 2x minus 4. And we want to find the equivalent polar equation. So once again, wherever we see a y, we're going to replace it with r sine of theta. Wherever we see an x, we're going to replace it with r cosine of theta. And then everything else will leave the same. And we're going to go ahead and solve for r. So to do this, we are going to subtract 2r cosine theta from both sides, and that will give us r sine theta minus 2r cosine theta is equal to minus 4. Notice we have a common factor of r, which we can factor out. And that will give us r times the quantity sine theta minus 2 cosine theta is equal to minus 4. Okay, now we can divide both sides by this particular quantity inside the grouping symbol, and that will give us the value the expression that we're interested in, or the equation that we're interested in, which is r is equal to negative 4 divided by sine theta minus 2 cosine theta. Now, if you're anal retentive like me, you might want to get rid of the negative sign in the numerator. So we could also write this as 4 times 2 cosine theta minus sine theta. So right here is basically a linear equation, in the expression for a linear equation in polar coordinates. Now the next part is to graph the polar equation and to represent or at least to find the graph that correctly represents it. And the hint is, you don't want to use this expression right here. That's just simply that is simply just too much work. What you want to do instead is use the original linear equation, and here it is. Now notice this is in slope-intercept form. We have a y-intercept of negative 4, so these two are out. Okay, and we have a slope of 2, or more specifically, a positive slope. This is a negative slope. This one is out. This has to be the graph. Okay, next we are going to want to deal with circles. So here we want to find the equivalent polar equation for this equation right here. And if you remember the stuff we learned in 115, or the equivalent course, you should realize that this is a circle that is centered at the origin and has a radius of 5. Okay, but nonetheless, we need to find the equivalent polar equation, and this can be a little tricky because it turns out that this maps to not just one equation but to 2 equations. But the first thing is we want to replace x with r cosine theta, so that will be r squared cosine squared theta. And then for y, we want to replace y with r sine theta, so that's going to be r squared sine squared theta, and that will be equal to 25. Of course, we have common factors of r that we could factor out, and that will give us the r squared is times the quantity cosine squared theta plus sine squared theta is equal to 25. Now take a look at this. This right here is our trigonometric identity, and this is equal to 1. So this reduces to r squared is equal to 25. And this is where you have to be careful, because when you take the square root of both sides, you are going to have that r is equal to plus or minus 25. 5 is the square root of 25, negative 5 is the square root of 25. As a consequence, we have 2 polar equations. The first one is r is equal to 5. The next one is r is equal to negative 5. And you have to put both equations in MML to get that answer correct. Now the graph, well, once again, this is the equation for a circle whose center is the origin and whose radius is 5. So this happens to be the graph. This is not the graph because, once again, the center is not at the origin and the diameter is equal to 5. The same with this. And this is not a circle. This is called a cardioid, which we'll be talking about in just a few minutes. Matter of fact, we're going to start talking about this now. So the next couple of slides, for the next few minutes, we're going to talk about common polar equations. And the first common polar equations are basically circles. For the case when r is equal to a, we will actually have a circle of radius a that is centered at the origin. For the case of r is equal to a cosine theta, you will have a circle where one end is at the origin, the other end is at x is equal to a, and of course what we will have is a diameter that goes along the x-axis, or a circle that goes along the x-axis and has a diameter of a. If a is positive, it will go in this direction. If a is negative, it will look something like this. Pardon my artistic ineptitude. So this would be if a is positive, or in this case a is equal to 1, but if a is negative, it will go in this direction. Similarly, for the case of r is equal to a sine theta, we once again have a circle. It is of diameter a, but if a is positive, it will go up the y-axis. One end will be at the origin, and it will go up the y-axis. If a is negative, it will go down the y-axis. But once again, a here in this scenario, a is the diameter, also here, so the radius would be a over 2. The next set of polar equations is called the Lemniscate, if I said it correctly. And it has to form r squared is equal to a squared cosine 2 theta, or r squared is equal to the a squared sine 2 theta. And actually it turns out that if you plot this, only half of the values actually basically are plottable. The other half will be the square root of a negative number, and there are no points associated with those particular values. However, it turns out that if we are dealing with cosines, we are going to have a figure 8. Here's our figure 8, and it will be oriented along the x-axis. And it kind of makes sense because, once again, when theta is equal to 0, 2 times theta is equal to 0, and we have, well, you guessed it, the cosine of that will be equal to 1, and we'll have maximum values. Now, one might think that for the case of sines, that this would be rotated 90 degrees, and the fact of the matter is, it is not. And it kind of makes sense. Just remember that when theta is 0, okay, well, 2 times theta is 0, and the sine of that is going to be equal to 0, which is basically why we have a null along the x-axis. But what about the case when theta is equal to 90 degrees? Well, then 2 theta is going to be equal to 180, and of course the sine of that is going to be 0, which is why we have a null here. Of course, when theta is equal to 180, we have a null. That's twice that is 360, so we have a null here. When theta is 270, twice that is 540, which once again results in a null. It turns out that when theta is equal to 45, 2 times theta is equal to 90, which is why we have a max here and also a max here. That's why we have 2 lobes, and it looks like they're rotated 45 degrees. The next polar equation is called a cardioid, and this is the one that I forgot to update. This should be a plus or minus a cosine theta, and this should be a plus or minus a sine theta. Notice that when we are dealing with cosine of theta, that the cardioid goes along the x-axis, and when we're dealing with sine theta, the cardioid goes along the y-axis. Furthermore, when a is positive, we have a null when theta is equal to 180 degrees. And that should make perfect sense, because when theta is equal to 180 degrees, cosine theta is -1, and we have 2 minus 2, which is 0. Similarly, we have a null at 270, and once again, when theta is equal to 270, sine of theta is equal to -1, we have 2 minus 2, and that gives us a null right there. Also notice that if a was negative, instead of going along the positive x-axis for cosine, it would go along the negative x-axis for cosine. And if a was negative for the sine, it would go along the negative y-axis instead of the positive y-axis. Okay, next we have limacons, which is essentially nothing more than a generalization of the cardioids. Cardioids is a special case of limacon when a is equal to b. Here, a is not equal to b. In this particular case, we have that b, the coefficient next to the cosine or the sine, is actually greater than a. And when that occurs, we get a little loop right here. Now, this right here is a plus b sine theta, which is why we're going in this direction. If it was a minus b sine theta, we'd be going in the other direction. But once again, since b is greater than a, we have an extra loop. Now, if it turns out that a is between b and 2b, we have not necessarily a null, but a bit of a dip at 180 for cosine and 280 for sine. But once again, and this right here is a graph of a limacon with a cosine term. If it had a sine term, it would be going in this direction. And then finally, if a is greater than 2 times b, what you actually have is basically a slightly distorted and skewed circle. This once again is a plus b cosine theta, where once again b is where a is twice as big as b, and if it was sine theta, it would be skewed in this particular direction. And then finally, we have Rose curves, and these are the form r is equal to a times cosine n theta, and r is equal to a times sine of n theta. Okay, now but it turns out that if n is positive, we will have, or if n is even and greater than or equal to 2, we will have 2 times n leaves. For example, here is 3 sine 2 theta, and we have 1, 2, 3, 4 leaves. Here is 3 cosine 4 theta, and we have 8 leaves. Now, if n is odd, then the number of leaves will equal n. So here we have 3, here we have 5. If you wanted to determine whether or not we are dealing with a cosine function or a sine function, you can look at theta is equal to 0. This is probably the best and only place to look to make that determination. If it turns out you have a null when theta is equal to 0, you are dealing with sine. If it turns out that you have a max when theta is equal to 0, you are dealing with cosine. Same thing here. Cosine at theta. Here we're dealing with cosine. we have cosine and we have a max when theta is equal to 0. Here we have sine and we have a max when, or a null when theta is equal to 0. Relative to your homework, what you're going to be asked to do is you're going to be given a function and you're going to be asked to choose the correct graph, okay, and then choose what type of shape it is. And here is our first one. The first one is r is equal to 1 minus sine theta. And if you notice, this actually has to form a minus a sine theta. That is the form of a cardioid. Not only that, since a is negative, that is going to be a cardioid going to go up or down the y-axis, not the x-axis. So this is out and this is out. Furthermore, since a is negative, that is going to be a cardioid that is going down the x-axis, which means it will be this cardioid here, not that. All right, our next one is a Rose function. Here we have r is equal to 4 cosine 3 theta. So essentially, since n here is odd, we are looking for a Rose plot that has 3 petals. This does not. This does not. Furthermore, we are looking for a cosine. Now when theta is equal to 0, we are going to have a max. Here, this one has a null. This one is out. This is the one that has to be the max. And then for our last trick, we are going to look at this function right here. Now once again, this here is a lemniscate. As a consequence, it is going to have 2 lobes. This has 3. This has 3. They are out. We are dealing with a sine, so this is going to be a graph of something that has 2 lobes that is rotated 45 degrees. This is along the x-axis. This is what we would get if this was cosine instead of sine. So this one is out. It has to be this one right here. And again, they'll be asking what kind of graph it is, and that would be the answer. So for our last trick, we need to convert a polar equation into a linear equation. And this is how this is going to work. First thing we want to do is we want to look at this particular equation. And notice that this is r is equal to a times sine theta. So this is an equation for a circle. It's going to have a diameter of 8, so the radius is going to be equal to 4. And since it's negative and we have a sine, the circle is going to be going down the y-axis. So this is 8, this is 0, and this should be the center, which is going to be 0, negative 4. Okay, so actually with just using this, we can actually figure out what the equation is. But we're not going to do it that way. We're going to do it the way using our polar coordinate configurations, or using our polar coordinate conversions. And we know that y is equal to r times the sine of theta. If that's the case, then sine of theta is equal to y over r, which makes sense. That's the definition of the sine of theta. So we can write r equals negative 8 sine of theta as r is equal to negative 8 y divided by r. And then we can write that as r squared is equal to negative 8y. We know that r squared is equal to x squared plus y squared. So we can write this as x squared plus y squared is equal to negative 8y. Now one thing that we can do is move the negative 8y over here. And if we do, we will have x squared plus y squared plus 8y is equal to 0. And since we know that we're going to be completing the square, maybe what we can, or since we have a circle, maybe we can complete the square and write this in circle radius form. So let's go ahead and do that. Notice here I have a linear coefficient that is 8. So what I want to do is I want to take that, I want to divide that by 2, which will give me 4, and then I want to square it. So I'm going to add 4 squared to this side of the equation. If I'm going to if I want to add 4 squared here, I need to add 4 squared to the other side of the equation. And that will give me that x squared plus, and then in parentheses I'm going to have y squared plus 8y plus 4 squared, and that is going to be equal to 4 squared. I could write that as 16, but it's more intuitive than 4 squared. Now this is a perfect square. And as a matter of fact, that is going to be equal to the quantity y plus 4 squared, and that will be equal to 4 squared. And I am where I want to be. This is a circle, an equation for a circle in center radius form. The center is 0, -4, as we expected it would be, and the radius is equal to 4. And with that, we can go ahead and recognize the correct plot for that equation. Once again, and this would be the correct plot. Once again, we can actually use our rectangular equation to figure that out. Or we could use this, because once again, this is going to be a circle of diameter 8 going down the y-axis, which of course would be this graph right here. This of course is a circle centered. This is a circle of radius 4 that is centered at the origin, so that's out. This is a circle going along the wrong direction, the y-axis. If this was 8 sine theta, this would be correct, but that's not what we're doing. And of course, this is a cardioid, so that is out as well. And that is all I have for this particular video. If you have any questions, please feel free to contact me. This is Bob Wood. Signing off.